chapter or something? 13? Sounds good. Why not? It seems like a good chapter, maybe. All right. So, chapter 13, we got into acids and bases. So, remember that the definition of an acid is something that has the ability to produce H plus ions in solution. So, the solution. And remember, when we're doing acid-base chemistry, H plus and the hydronium ion, which is H3O plus, they're basically used interchangeably here. Again, both in formulas and equations, they basically represent the acid part of the solution. And a reminder that in order for something to sort of be an acid, it does have to have that ability to actually produce free floating H plus. Again, not attached to anything, just kind of floating by itself. So the more H plus is able to kind of produce, the better acid it is. A base, on the other hand, is something that can produce hydroxide ions in solution. Same idea there. It needs to be kind of free floating hydroxide ions, not attached to anything, just kind of floating around freely in the solution to be able to do that. Now, a more sort of generic or general definition of an acid and a base is the Bronsted-Lowry definition. And in the Bronsted-Lowry definition, an acid is a proton donor, and a proton is another name for an H plus. So it's something that will give away a proton to something else. And a base is a proton acceptor. And as we talked about at the end last time, sort of the Bronsted-Lowry definition does create sort of partners or pairs as a result of that relationship. So when you have an acid, say like HCl, and it's going to dissociate in water. In this particular case, obviously the acid here is going to be the HCl. The water is actually going to act, in this case, as the base, which means the acid is going to send the H plus over to the water. The result of that is we will then form H3O plus when it accepts the hydrogen ion, and Cl minus on the other side. And again, our acid there is the HCl, our water pretty much working as a base. Let me label that as a base, maybe. And they do create partners on the other side. So the HCl in this example, again, its sort of partner on the other side is known as the conjugate base. So the acid on one side, its partner on the other side is going to be known as conjugate base. And the base on one side, its partner on the other side will be the conjugate acid. So as we talked about last time, your kind of regular acid and bases will be found on the left-hand side of the arrow, all your conjugate sort of partners on the right-hand side of the arrow. And once again, the absolutely only difference that there can be is one H plus difference between those things in order for them to be considered bases. So if you have anything, again, that is greater than one H plus difference, they would not be considered bases. As we go from the acid to the conjugate base, it has one less H plus as it loses it. And obviously, as we go from the base to the conjugate acid, it has one more H plus. We also talked about amphoteric substances last time. And water is such a substance. An amphoteric substance is a substance that can act either as an acid or a base. Water can do that. As I mentioned before, things typically with a hydrogen, like a negative charge, also has the ability to kind of do that. Things like bisulfate, bicarbonate, they tend to have the ability to kind of go both ways because they do have a hydrogen they could give, and they also have a spot to sort of accept the hydrogen in, so they could kind of do both things along the way. Any questions on any of that stuff there from last time? All right, then let's continue. All right, so for each of these here, decide if any of these are conjugate acid-base pairs. So take a few moments there and look at each of those sort of pairs and see if they are related to each other in the conjugate acid-base pair combination. Okay, so let's take a look and see. So the one thing you want to keep in mind when you're trying to determine if these are related to each other, again, this is the only difference. Basically, just one of those is the only difference that there can be. So when we look at the first sort of combination there, we got HCl and we got, I hate when books write it like this, ClO minus, which is hypochlorite. And obviously here, the difference between these two is an H plus. You can put one on the guy on the right or take one on the one left. But the problem is there's also a difference of obviously an oxygen here in the one on the right and not on the left. So that would mean no pairs there because we have a difference of a hydrogen and an oxygen, not just the hydrogen. So it's got to be only the hydrogen. We take a look at the SO4 and a little SO4 2 minus. Are these guys pairs? These guys are not pairs either because the difference here is not 1H plus, it's actually 2H plus difference between those two, and that does not make them pairs. They are related to each other, and you may be wondering, how come they maybe are not pairs? So when we look at something like that, H2SO4, as you might remember from previous semester, is what they call a diprotic acid. Diprotic acid means that it has two hydrogens to give, right? As opposed to a monoprotic acid, which has one hydrogen to give, or perhaps a triprotic acid that has three hydrogens to give. Now, when you get into sort of a diprotic acid or a polyprotic acid, triprotic acid, the hydrogens actually come off one at a time. So they don't both just drop off into the solution at once. It's actually a stepwise formation as to which they will give away their hydrogens. So really the first thing that happens in this situation is the sulfuric acid will give away one hydrogen. And then this guy here, the bisulfate, will give away another hydrogen and become sulfate there. So when we look at sort of relationships between these, this guy here and the bisulfate, they are partners, as the only difference between those two is 1H plus. The bisulfate there and the sulfate are also partners, as again, the only difference there is that 1H plus. But when we jump from kind of our beginning guy down to the end, we are leapfrogging too many hydrogens in that case, and they are not considered pairs at that point. So they happen to be related to each other, but because, again, the difference there is the HSO4 minus, that's really what ties both of those together to be pairs. Any questions on that there? When we look at the third one here, we got a little NH4 plus and a little NH3, and the difference between these two is 1H plus. And you could either put the H plus on this guy and you end up with this one, or you could take the H plus off of that one and you end up with that one. So that would be a pair there. And H3O plus and OH minus, these guys are not pairs. Again, it is more than one H plus difference. So they would not be pairs. What really ties them together that would be pairs with both of them is our friend water would actually be pairs with both of them. He would be related to that guy, and the difference is that one H plus difference in that case. Any questions? And obviously that can't be it since number 3 was good. Yeah. Any questions on that there? So let's take a look at this one. Aniline is C6H5NH2. What would the conjugate acid be in this case? Okay, so hopefully you know in this situation we're only talking about an H plus. The real key is should you put it on or should you take it off, depending on what the problem is. So understanding the relationships that we talked about earlier, which is if you have an acid plus a base on one side, they will have a conjugate acid on the other side and a conjugate base on the other side. And the acid on this side is related to the conjugate base, and the base is related to the conjugate acid. So they were nice enough in this problem to tell you, but in case they didn't and they just asked you, what is the conjugate acid? That means you want to end up over here. And if you follow that arrow backwards, that means what you are looking at is a base. And all you have to do is follow the Bronsted-Lowry definition of a base, which is it should actually accept the H plus. So in this case, we should put the H plus on and everything else stays the same. So a little C6H5NH, and I'm going to add one H. As we also talked about last time, it's not just a hydrogen, but it has a positive charge, so that affects the charge of the overall thing. So this guy was neutral to begin with. We added an extra positive charge, so it will end up with a positive charge as well. And I think that's number 2 there, if I'm not mistaken. Yeah. Any questions on that one there? Now, let's say we had HCO3 minus, a little bicarbonate. Why don't you write the formula for the conjugate acid starting with it? And why don't you also write the formula for the conjugate base? Okay, so again, we can kind of use our relationships to figure it out. So if we want the conjugate base, we're going to end up here. So if I go all the way back, what I am looking at in this case is it's going to behave as an acid. Again, the Bronsted-Lowry definition of an acid is it should donate the H plus. So that tells us we should take the H plus off of this. So as we go from there to there, we're going to subtract the H plus. That's going to leave us a CO3. And when we lose a positive charge, we become one more negative. So it started at -1 and will end at -2 in this case, and we'll make carbonate. Any questions on that there? Now, same deal on the other one, kind of like the problem we did here. We're looking for our conjugate acid, which is here. And again, if we kind of follow it backwards, that means in this particular case, it is going to act as a base. And again, the definition of base, we're going to accept the H plus there. So we're going to do a little H plus action there. So when we put the H on there, we get two H's, a C and an O and a 3. +1 and -1 equals 0. So we now become one more positive and become neutral in this case and make carbonic acid. This is another example of a substance that can act as both an acid or a base, depending on the situation. This is an amphoteric substance. We will later on talk about how you can decide which it may do. Will it act as an acid or a base? But it does have that ability. And like I said earlier, it's typically things with a hydrogen and like a negative charge. A lot of times those guys have that ability to kind of go both ways because, again, they have the hydrogen and they can accept the hydrogen. Any questions on conjugate acid bases? Now, water, as we talked about previously, is definitely an amphoteric substance. And water itself can actually react with other waters. And that's basically what's happening when you have water. So in this case, one water will act as the acid, the other water will act as the base, and we're going to get a removal of a hydrogen from one. So I'll just draw it this way. So the hydrogen is going to go over there, which means this guy would be our base. This guy would be our acid in this example of my arrow. And we will end up with our conjugate acid and conjugate base on the other side. This is what is sometimes referred to as the autoionization of water. This sets up an equilibrium as I see two arrows pointing in the same direction. And because it's a reversible reaction, we could write our favorite thing ever, which is an equilibrium expression for this. We're going to do our products over reactants like normal. So the concentration of H plus times the concentration of OH minus. This is actually a special equilibrium. It is creatively called Kw because I'm assuming it involves water, which make what the W would stand there for. This is the equilibrium constant for water. We do not include the reactants because, once again, it is a pure liquid and it's not included in the equilibrium expression. This equilibrium value, this equilibrium constant actually has a value that is commonly used, which is concentration of H plus times the concentration of OH minus equals 1 times 10 to the minus 14. Now, you could also, as I mentioned earlier, because this is acid-base chemistry, you will very often and probably in books see Kw written as such, H3O plus and OH minus is equal to 1 times 10 to the minus 14. So once again, this H3O plus and this H plus are pretty much the same thing. So I'll be honest with you, I personally use H plus most of the time. Books and stuff will use H3O plus. Again, you're welcome to use whichever one you want. The H3O plus would actually come from this sort of a formula where we show the two waters reacting with each other. The H plus would come from this one. They're both really the same reaction. Again, the other one just has that extra water in it. Kind of like what we talked about with the acid early on, where if you take the acid plus the water, you'll get the H3O plus, or you could just show the acid breaking apart into H plus and Cl minus, for example. So it's very similar. So basically what this is the ion product of water. And basically here we have our 1 times 10 to the minus 14. So we basically have our acid part of the solution and our base part of the solution. And we could use this to calculate one or the other depending on which one you're given. The good news is it's pretty much the same calculation regardless of which one you're given. So if you want the H plus concentration, you're going to take 1 times 10 to the minus 14, which is for the most part a constant value, divided by OH minus. Or if you have the opposite and you want the hydroxide concentration, you can do the same thing. 1 times 10 to the minus 14 divided by the H plus concentration. You definitely want to be using your exponent button when you punch this stuff in this chapter for sure. Now, I say that 1 times 10 to the minus 14 is most likely 99.9% of the time the number that you would use for Kw. The reason I say most of the time is it is still an equilibrium constant, right? And as we talked about, the one thing that can affect the value of an equilibrium constant is what? What affects it? Temperature, yeah. And technically speaking, if you're doing a problem where the temperature is not 25 degrees, then technically your Kw value would probably be a slightly different number than what you see there. But I would say most of the time it's pretty safe in book problems and most problems, even if they don't give you the temperature, to assume you're doing it at 25 degrees and you can use this 1 times 10 to the minus 14. Typically speaking, if you come across a problem in a book or something like that, where it's not at 25 degrees, they will either tell you to go look it up in a table or they may even give you a different Kw value to use. But again, almost 100% of the time, you can probably roll with that number. You'll be in good shape. But there are certain situations where you might actually see a slightly different number for it because the temperature is not 25 degrees. So what can we do with this? We could compare the concentration of the H plus, which is the acid part of the solution, to the OH minus concentration, which is the base part of the solution, and it will tell us whether or not our solution is acidic, basic, or neutral. So if you calculate the H plus concentration and it actually equals the OH minus concentration, which, by the way, that would be a concentration of 1 times 10 to the minus 7 for each, it will be a neutral solution. If you calculate the H plus concentration and it's larger than the OH minus concentration, so your acid part is bigger than your base part, the solution will be acidic. And if you calculate the OH minus concentration and it's larger than your H plus concentration, then the base part of the solution is bigger than the acid part of the solution, and that solution will be basic. So we could kind of use the H plus and OH minus concentrations to allow us to determine what type of solution we're dealing with. Is it acidic, basic, or neutral? Any questions on that there? All right. Let's try 14. In this case, we are given the H plus concentration of 1.3 molar, which means we could rearrange this. And like I said, it's pretty much the same calculation regardless of which one you're given. 1 times 10 to the minus 14 divided by our H plus concentration of 1.3. Once again, I want to make sure you use your exponent button, 1 exponent button, negative 14 divided by 1.3. That's going to yield us here perhaps a 7.7 times 10 to the minus 15 molar in this case. Yeah. Questions on that? This would be, by the way, acidic, basic, or neutral? The H plus concentration versus the OH minus concentration, which one's larger? That's not the trick question. It is the H plus concentration, I hope, yes. 1.3 is much larger than something to the minus 15, I would assume. So it should be acidic. That also should be acidic because, frankly, it's a hydrochloric acid solution. So I would hope it would end up in the acidic range. Would be a good thing, I suppose. All right. Let's try this one here. The H plus concentration is 1.2 times 10 to the minus 6. What is the OH minus concentration, and is it acidic, basic, or neutral? So take a couple minutes there, see what you get. Okay, W it up, and little H plus, little OH minus concentration. Going to equal 1 times 10 to the minus 14. In this particular case, again, we're given the H plus concentration. We're looking for the OH minus concentration. So OH minus, once again, will equal our 1 times 10 to the minus 14 divided by the H plus concentration given to us, 1.2 times 10 to the minus 6. And if we do that there, you're going to end up with 8.3 times 10 to the minus 9 molar. Or if you do not have your calculator in scientific notation, maybe a bunch of zeros with an 8 at the end of your screen there, just kind of hanging out. Again, if you put in scientific notation, you'll get to 8.3. Now, when we look at that, that obviously eliminates those two. We're going to now compare our H plus concentration to our OH minus concentration. And in this particular case, our H plus concentration, obviously there was 1.2 times 10 to the minus 6 molar. By the way, since this is a concentration that we solve for, you do need some units there. Yeah, that's a molarity. Which one's larger, the H plus or the OH minus? It is the H plus, yeah. So the H plus is larger here, and that would mean it would be acidic. A reminder that when you are comparing negative exponents, the smaller negative exponent is the larger number because to the minus 9 means we're going 9 places that way and adding zeros, right? Which makes it a much smaller number than only going 6 places that way and adding zeros, right? So when you're comparing those negative exponents, smaller negative exponent is the larger number when you look at it. Any questions on that there? All right, then the next thing we're going to talk about is pH and the pH scale. The pH scale runs from 0 to 7 to 14. So a little 0 to 7 to 14 action. Below 7 is acidic. Above 7 is basic. And really right on 7 is neutral. And that is because at 7 or neutral pH, the H plus concentration will equal the OH minus concentration, and that will get you really a pH of 7. So we're going to go 7 as being neutral here. If it's a little bit above 7, that's going to be slightly basic. If it's a little below 7, it'll be slightly acidic. To 7 is sort of our middle point. As you go towards 0, you're becoming more acidic. And as you go from 7 towards 14, you're becoming more basic. To calculate the pH, we could use that formula there. pH is equal to minus the log of the H plus concentration. This is, again, another formula, if you would like, that you could substitute in H3O plus in there. So same idea. The actual name of the formula tells you what you need to calculate it. pH means you need the H plus concentration to calculate it. Now, if you calculate the solution and it gets you a pH of 7, as I mentioned, your H plus and OH minus concentration are going to be equal to each other. Again, less than 7 is going to be acidic, and greater than 7 there is going to be basic. Now, when we use these formulas in your calculators, depending on what type of calculator you got, as to how you should punch this formula in, and probably others that we come along. So if you have a display calculator, you're going to punch it in exactly the way it's written. Remember, you're not going to use your subtract button, but you're going to use your negative button on your calculator, your plus minus or the in parentheses little negative button. You're going to hit the log button, and then you're going to put your number in, probably with a little exponent action, right, as you punch it in. If you have a non-display calculator, you actually have to go backwards in this formula when you punch it in, and all other formulas we're going to talk about in this chapter. You would actually start with the number, which you would probably punch in with your exponent buttons. You would then hit the log, and then you would hit the negative button. So display, you go in this direction. Non-display, in terms of the formula, that's how you punched in. If you're not sure what type of calculator you got, you just hit the log button. If it says log on your screen after you do that, congratulations, you have a display calculator. If it says error on your screen, congratulations, you have a non-display calculator, and that would be a really quick way to figure out which type of calculator you have. Any questions on that there? Now let's talk about everybody's other favorite thing, which is significant figures, and when you do a calculation like pH. So for example, the number of decimal places in a value like pH should equal the number of significant figures in the concentration value. So in this case, if you have the concentration, however many significant figures are in the concentration is how many decimal places your pH value should have. So for example, if we had an H plus concentration of 1 times 10 to the minus 5 molar, calculate the pH there to the proper number of digits. Draw your calculator out, make sure you know how to punch it in, would be good. Calculator on this one, you would go the negative button, you would go the log button, you would type in 1, you would hit your exponent button, you would hit your negative button, and 5, and hit the equal button. You have the non-display calculator, you would start with the 1 and the exponent button, the negative button, and 5. Then you would hit the log button, and then you would hit the negative button one last time. And that should give you a 5 staring at you on your screen, hopefully. Now, should my pH be recorded as 5, 5.0, 5.00? What is the correct way to record the pH in this case? It actually should be 5.00. Should actually be this one here. And not that one, not that one. This is our concentration value, and a reminder, as we talked about perhaps, or we'll talk about everything that is before the times 10 part, right, is significant. So this concentration value has 2 significant figures. Now what we're looking at here is not significant figures to significant figures. We're looking at 2 significant figures to decimal places. So the 2 significant figures gives us that many decimal places. By the way, we're going to talk about going the other way from the pH back to the concentration unit, and you follow the same rules. So if your pH value had 2 decimal places, when you calculate the concentration, you should end up with two significant figures. But again, it's people always get this confused. They think it's always like sig figs to sig figs, but again, it's sig figs to decimal places in this case. By the way, this one would be acidic, basic, neutral. Acidic. This is acidic as it is less than 7. And that's always, by the way, I would always look at the pH value if you have it in terms of acidity. If it's acidic or basic, as the pH scale is usually the one most people have in their head. So that's usually the good one to look at. Any questions on that there? By the way, the relationship as well is the pH goes up as the H plus concentration goes down. Another important relationship is the one between H plus and OH minus. They are opposite relationships. So as the H plus concentration increases, the OH minus concentration will decrease. So as one goes up, the other goes down, and vice versa. As the H plus concentration would decrease, you would see an increase in the OH minus concentration. So the more H plus that you have in the solution, the lower the pH will be and the more acidic it will be. The more hydroxide you have in the solution means you have less H plus, and that will then make it a higher pH and probably heading towards the basic range. And again, they are opposites to each other. So you build up that hydroxide, you're going to really lower the H plus concentration, and vice versa as you add. Here is the pH scale and some things on it. Here we have sodium hydroxide, which is a strong base up there by 14. Our strong acid down there by 0. We have vinegar, lemon juice, obviously stomach acid. That's all acidic stuff. We got some blood there, slightly basic. Got some pure water, which is 7. By the way, if you did not have pure water, would the pH be 7? It will probably not be. People are sometimes surprised. It'll probably be down in that range, right about there. And that is because, especially if you have water just sitting out, it sometimes will pick up CO2 from the air and make carbonic acid, which will increase the H plus concentration and lower the pH along the way. That's why sometimes if you ever need like neutral water, not so much in these nice fancy new buildings, but if you ever were in a lab that was a very old building, they oftentimes when they do like your titration experiment, they would have you boil the water to get rid of the CO2 in it, bring the pH back to the water closer to neutral before you made like your sodium hydroxide solution you did there in 200A. But now they have nicer insulated sort of buildings that they don't have to worry too much about that. They don't know how you make you do that too much along the way. This right here is the classic Beckman pH meter there. Still have a building over in Brea before they make, but it's still over there. But actually, that's how he kind of started. He made a pH meter, Beckman, and a pH meter is basically an electrode and it measures the H plus concentration in a solution. You basically calibrate it. It usually works through voltages. You give it like, hey, this voltage represents a pH of 4. This one represents a pH of 7. This one represents a pH of 10. Makes like a calibration curve. So then when you put it in your solution, it can sort of figure out based on the voltage in your calibration curve how much H plus is in there. And another sort of scale, though, that is similar to pH is actually the POH scale. And much like the pH scale, it does run from 0 to 14, but it is different. And once again, here, the POH, the name actually tells you what you need. In order to calculate the POH, you need the OH minus concentration. Just like to calculate the pH, you need the H plus concentration. Now, the POH scale runs from 0 to 7 to 14. Less than 7 is basic on the POH scale. Above 7 is acidic, and 7 is still neutral there on the POH scale. Now, a reminder, as we just saw there, our pH scale is opposite 0, 7, and 14. less than 7 is acidic, and greater than 7 is basic. They are opposites of each other. So if you have a low pH, you will have a high pOH, and vice versa. And a nice relationship between pH and pOH is if you take the pH and you add it to the pOH, it will equal 14. So this is very helpful. For example, if you're given the hydroxide concentration and you want the pH, you could calculate the pOH and then subtract 14, and you will have your pH there by just doing so. So it's very helpful. Now, when you're asked a question, for example, of is this solution acidic, basic, or neutral? By the way, when you are asked that question, there is only one answer. The solution cannot be acidic and basic at the same time, although in a lot of exams and quizzes, I have seen that answer that the solution is acidic and basic at the same time. I've never seen anybody give all three, I think. I don't think I've seen anybody give all three for the same solution. Now, why would people do that? Perhaps for the same solution, say it's acidic and basic. The reason is they calculate the pH and go, cool, it's above 7, it's basic. Then they calculate the pOH and go, cool, it's below 7, it's acidic. And now this one solution is both things at the same time, which they cannot be. So my piece of advice would be, since most people don't really think about the pOH scale, most people have the pH scale in their head. I once again would always go back to the pH value and use that to determine whether it's acidic, basic, or neutral. So you don't give a funny answer like that, right? That I probably don't want to see on an exam or quiz when you give it. Now, with this, it does give us a variety of ways that we could sort of solve some problems. Since we got a little room over here, we'll add our KW in that we saw earlier, which is our H plus and our OH minus, equaling 1 times 10 to the minus 14. Now, a couple other calculations that you can do is if you actually do have the pH value given to you, directly from the pH value, you could calculate the H plus concentration. So if you have the pH given to you, you can directly calculate the H plus concentration by taking the inverse log of the negative pH. On most people's calculators, when you do the inverse log, it usually pops up a 10 and a caret, and you go negative pH. You can also, if you have the pOH given to you, from the pOH, you can directly calculate the OH minus concentration. And it is the exact same calculation. The OH minus concentration would equal the inverse log of the negative pOH, which once again, on most people's calculators will pop up a 10 and that caret. And again, you're going to do negative pOH here. How do you get the inverse log of most people's calculators? Upper left corner, there's like a second button, maybe it's a shift button, and you usually should have a log button that has a 10 to the x, also known as how a lot of people incorrectly put scientific notation into their calculator, which would again, I'll repeat the fact that you should definitely make sure you're using your exponent button to do this chapter. Otherwise, you're going to compound your calculation terribly and you get the wrong answer if you're not doing correct scientific notation and you try to use something like that. Same thing with those formulas as well. If you have a display calculator, you would punch it in exactly the way it's written. You would hit the second button, top left corner, or shift and log. It'll pop up a 10 and a caret. You hit your negative button and then put your pH or pOH value in. If you have a non-display calculator, you have to still work backwards. So you would start with the number, you would make it negative, and then hit second log, and then it will do it for you. So once again, same sort of rules for these calculations here. You got the display calculator. You're going to go seconds or shift. You're going to go log. You're going to go negative and your number. You have the non-display. You're going to go your number. You're going to hit the negative button. You're going to hit the second button and then you're going to hit the log button. So once again, that would be the way to kind of punch it into your calculator and hopefully get the right answer. So this is like your chart here of everything calculus acid and bases, how to calculate the pH, POH, the relationship between them, our KW we saw before, from the pH to get the H plus and to get the POH. This, as I was mentioning earlier, does give you a variety of ways to get to the answer. You could get all the answers you probably want without using KW. You could still use KW like we did earlier if you want the H plus or OH minus concentration. So it just kind of depends on your route as to how you want to calculate some of these. They all should give you the same answer as long as you obviously punch them in correctly and use a proper formula. Any questions on any of those there? Okay. All right, then let's just do it all to make sure our calculator works, right? So we have a pH of 4.82. What is the POH? What is the H plus concentration? What is the OH minus concentration? And is it acidic, basic, or neutral? And for the bottom one, we have a hydroxide concentration of 2.5 times 10 to the minus 7. Okay, so let's take a look and see. We'll start with the first one here. So we were given the pH here. So really, since we were given the pH, we really have two options since we're looking to solve for everything. We could definitely get the POH from that. We could also use it to get the H plus concentration. So again, it's your call, whichever way you kind of want to attack it first. I'm going to just get the POH here. So the pH plus the POH is going to equal 14. That means my POH will equal 14 minus my pH there, which is 4.82. And that's going to get me a POH of 9.18. At this point, we can still use the pH to get the H plus. We also have now the POH, which we could get the OH minus from as well. So I'm going to go H plus concentration. So using the pH, once again, we can directly get that H plus concentration. It is going to equal the inverse log of the negative pH. So once again, when you punch that on your calculator, usually you'll see something like a 10 and a caret, and then a negative. Again, do not use your subtract button, use your negative button, 4.82. And if you do that there, negative 4.82. Looks like we end up with 1.5 times 10 to the minus 5 molar. We do need a concentration unit. By the way, here we are going from two decimal places back to two significant figures. Again, going backwards from pH or POH to it. At this point, it actually opens up one more option for you. Now that you have the H plus, you can also use KW like we did earlier to get to the OH minus, or you can do the same calculation with the POH. Once again, they both should really give you the same answer. So I'll do the newish calculation there. The POH, once again, will get you the OH minus by taking the inverse log of the minus POH. And again, that's going to look something like this on your calculator. 9.18 negative. Grab your calculator maybe. And negative 9.18. Going to yield me a 6.6 times 10 to the minus 10 molar. And again, like I said before, you could have used KW at this point, and you will get essentially the same number. Maybe it's slightly different with rounding, but should pretty much be pretty close to the same number. At this point, we want to know, is this acidic, basic, or neutral? Again, I'm going to look at our pH value, which is 4.82. That's less than 7. That's going to mean acidic in this case. Yeah. Any questions on any of those there? All right. So taking a look at the bottom one here. In this case, we are given the hydroxide concentration. So since we are given the hydroxide concentration, we can either calculate the POH directly from that, or we could use that to get to the H plus concentration. So once again, it is your option as to which way you want to go. I will actually use KW for a little throwback action here. We'll do a little H plus and OH minus equaling 1 times 10 to the minus 14. So solving for H plus, 1 times 10 to the minus 14 divided by our OH minus concentration, 2.5 times 10 to the minus 7. So that's going to get me here. Looks like 4.0 times 10 to the minus 8. Again, it's going to be molar. At this point, we just need some pH and POH since we have both the H plus concentration and the OH minus concentration. Our pH will equal negative log of the H plus concentration, which we just calculated. So negative log of 4 to the 8, it looks like. And that's going to get us here. Looks like 7.40. And now that we have the pH, I could simply just take 14 minus it, and that will get me to my POH with not too much work there. And that's going to give me a 6.60 in this case, right? First off, any questions on those calculations there? That would mean that this solution, once again, looking at the pH value, slightly above 7. So this would be basic in this case, slightly basic in that case. Any questions on that there? All right, one last one here to finish it up on. We have an environmental does something chemist, rainwater. H plus concentration, 3.5 times 10 to minus 6. Once again, calculated everything there and determine acidic, basic, or neutral. All right, so in this case, we have the H plus, so we're looking for everything. I'm just going to go pH first here. So with the pH, we could just go right in and minus the log of 3.5 times 10 to the minus 6. And looks like a 5.46, I think, as our pH. Now that we have the pH, we can just subtract 14 to get to the POH. So that's going to be 14 minus my pH value there. So 14. Going to get me 8.54 as my POH. Now, in this case, I do need to do my inverse log here to get the OH minus concentration, now that I have that. I could have also used KW as well, since I did have the H plus concentration. So we'll go OH minus is equal to the inverse log of the negative POH, which again will do something like this. And looks like maybe 2.9 times 10 to the minus 9 molar. Again, need a unit on that. And lastly, looking at our pH here, which is 5.46, that is less than 7. Looks like an acidic solution. Any questions on how to calculate pH, POH, H plus, OH minus concentrations? All right, we're laid up there for today.